Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. In the last video, we worked on basic transformations of sine, cosine, and tangent graphs. Today, we're going to step it up to intermediate level. We're going to be applying transformations in more complex ways, including reciprocal trig functions and a more conceptual problem. By the end, you'll be comfortable reading, sketching, and interpreting transformed trig functions. So let's get started with our first example. We want to sketch the graph of y is equal to 3 times sine pi x. So a quick refresher, the general form is y is equal to a times f of b times x minus p plus q. So here, our a value is 3, which is the amplitude, and our b value is pi, our p value is 0, and our q value is also 0. So this tells us we have no horizontal and no vertical translations. And then using the b value of pi, we can go ahead and find the period of this function. So our period is equal to 2 pi divided by our b value, which is pi, which means the period of this function is equal to 2. So on our graph, let's say that this is 1 over here, and this is 2. And since our amplitude is 3, that means we're going to draw our maximum line at y is equal to 3, which will be up here. And then our minimum value is going to be at y is equal to negative 3. So let's go ahead and label these. That'll be 3, and this is negative 3. So since we have no phase shift, we're going to start at the origin, just like the original sine graph. And then we're going to complete one full cycle at 2, which means we're going to hit our maximum value at 1/2. We're going to go back to 0 at 1, and our minimum value is going to happen at x is equal to 3 over 2. And now we can go ahead and draw our curve, which is going to look something like this. So this would be one full cycle of this sine graph. And we're going to do the same thing on the left side. So that'll be negative 1 here, negative 2 there. And it's going to be 0 at negative 2 and negative 1. We're going to have our maximum at negative 3 over 2. And then our minimum is going to happen at negative 1/2. So the second full cycle is going to happen right over here. Next, we're going to take a look at how to sketch a reciprocal trig function. So recall that the secant function is just 1 over cosine. So this means that anywhere where cosine is 0, we're going to have a vertical asymptote. So let's say that this was our pi over 2, and this here is pi, and this here is negative pi over 2, and this here is negative pi. Then the original secant function is going to have a vertical asymptote at pi over 2, and then another vertical asymptote at negative pi over 2. And then the y value here is 1, so it'll start at 1, and then it's going to look like a bowl right over here. And then it's going to have another vertical asymptote at 3 pi over 2. And here, this is negative 1, and it's going to be a downward facing bowl right over here. And then same thing on the left-hand side. So this would be negative 3 pi over 2. We're going to have a vertical asymptote here. And then we have our downward facing bowl right over here. So this would be the graph of the original secant function. Now for this transformed secant function, let's go ahead and write down our important values. So we have a is equal to 2. Our b is equal to 1. Our p is equal to pi over 3. And then our q here is equal to 1. So what the q value tells us is that our midline is now at 1. So let's go ahead and draw that. That'll be right over here. And then because the a value is now 2, everything is going to be stretched vertically by a factor of 2, which means these points are now going to be 2 units away from the midline. So they're going to be right over here, and right over here. But because our p here is pi over 3, they're also going to be shifted pi over 3 units to the right. So all of them are going to be moving over to the right by pi over 3 units. And pi over 3 on our graph is right over here. So this is pi over 3, this is 2 pi over 3, and then this is pi. So this here would be negative pi over 3, negative 2 pi over 3, and then negative pi. So we're going to take those 3 blue dots and move them pi over 3 units to the right. So that means they're going to be here, here, and over here. And same thing with these vertical asymptotes, they're also going to be shifted pi over 3 units to the right. So that means our new vertical asymptotes are going to be right here, right here, right over here, and right over here. Now the spacing between these vertical asymptotes stayed the same because our b value here is 1, which means we didn't have any horizontal compression or expansion. So this transformed secant function is going to look like this. So the blue graph is our transformed secant function. So I'm going to make the new transformed function a little bit thicker so that it stands out a little more. The gray graph we've drawn is the original secant function, and then this blue one is the one that we're working on for this particular example. Now for our last example, this one came directly from the 2023 IB exam. So we're given that our function f of x is equal to sine of q times x, where q is a number that is greater than 0. Now this diagram here shows the graph of f for the range 0 to 4m, where x is in radians. And we can see that we have x-intercepts at 0, 2m, and 4m. So we can see that this is one full cycle of our sine function, f of x. Now, part 1 of the question asks us to find an expression for m in terms of q. So since we know that one full cycle is 4m, or in other words, the period of this function is 4m, we can use that to relate our m and q. So since our function f of x is equal to sine of q times x, that tells us the b value here is q. And our period is equal to 4m, but we know that that is equal to 2 pi over our b value, which is q. So now, if we were to isolate m, we get m is equal to 2 pi over 4q, so m is equal to pi over 2q. Now part b says we have another function g of x, and it's equal to 3 times sine of 2qx over 3. And we want to sketch what this graph looks like for the interval x between 0 and 6m. Now, there are a couple of different ways to do this. We can use the relationship between the period and the b value to calculate what the period is for this new function g of x. Or we can actually just rewrite g of x as g of x is equal to 3 times sine of, I'm going to take the 2 over 3 out in front, and then I'll leave the qx after. So why am I doing this? Well, if you look at our original function f of x, our f of x was sine of q times x. So all I'm doing here is I have this new factor of 2 over 3 in front of q times x. So using our knowledge of transformation, we know that this 2 over 3 in front is going to be a horizontal stretch of 3 over 2 from our function f of x. So this tells us it is a horizontal stretch by 3 over 2 from the original function f of x. And then this 3 in front of sine is a vertical stretch by a factor of 3 from f of x. So since this black graph on the screen here is what our f of x looks like, we know that our g of x is going to be stretched horizontally by a factor of 3 over 2 from this graph here. So that tells us we are going to have a period of 6m. And since we have no horizontal shift, that means we're still going to start at the origin. And then halfway between 0 and 6m, we're also going to be at 0. And then our maximum is going to happen halfway between 0 and 3m, which is right over here. And because we have a vertical stretch of 3, our maximum is going to happen at 3, which is up here. And then our minimum is going to happen at a next value that is halfway between 3m and 6m. And it'll have a y value of -3. So therefore, the graph for our g of x is going to look like this. Now, just as a quick side note, if you wanted to solve this using the relationship between the period and the b value, you can also do that. So that would give us the period is equal to 2 pi over the b value of g of x, which is 2q over 3. So simplifying that, we get this is equal to 3 pi over q. Now, we can go ahead and isolate q from this equation here. So if we do that, we would get q is equal to pi over 2m. And substituting that back into there, we get this is equal to 3 pi over pi over 2m. So this is equal to 6m. So this would have told us that our period for our function g of x is equal to 6m, which is exactly what we got using our first method. And now let's go ahead and do a quick recap of what we covered in this video. So from the first example, we saw that the period doesn't have to be in terms of pi. We can still perform transformations as we normally do. We saw how transformations of trig functions can also apply to the reciprocal trig functions as well. We just need to know what the originals look like. And most importantly, don't lose sight of the fact that we're still performing transformations here. So even though we've introduced new terms like the amplitude and midline, these transformations are still performed in the same way as before. So by thinking about it in terms of the actual transformations instead of the properties of the trig graph, it may be easier to gather enough information to complete the picture. And now it is your turn to give this a try. Can you sketch the graph of the transformed trig function on the screen here? Let us know how you did in the comments below and whether or not you'd like to see more content on trig transformations in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.